In this screencast, we will look at performing a degree of freedom analysis on a multiple unit separation process. Performing a degree of freedom analysis is an important first step in analyzing a system and determining whether or not the conditions are fully defined. Now imagine you are being tasked with designing a process to meet certain specifications, and you spend countless hours trying to determine why you cannot meet those specifications given certain conditions of that process, all to find out that too much information was given and the information didn't correlate correctly. Or what if not enough information is provided and you cannot fully design that process? To solve that problem, we're going to perform a quick degree of freedom analysis that could give us this kind of information before any calculations are even written out. So let's look at the case here for a tandem setup of absorbing and stripping columns. We have an absorbing column here on the left, and we have a stripping column here on the right. So I've redrawn this process into a block flow diagram and labeled known information about a certain process. And the question is, can we determine the unknown parameters? Now, one thing about this process you might have seen is the spent solvent line. And so, we're recycling this absorbent. At some point, we have to dump it, and so there may be a valve or something to control that release. We're going to negate that here in our process. So we have our block flow diagram. We have our labeled streams, and this is the first place to start given any kind of problem. So to start the degree of freedom analysis, we have to choose an appropriate boundary to analyze. Now, we could do a couple different things here. We could choose to analyze the overall system. So this would include both units, and we would draw our boundary here. Thus, we would look at any streams that cross that boundary and forget about any streams within that boundary area. So this would be our overall process. We could also do a degree of freedom analysis just around the absorber, or we could do one just around the stripping column. Sometimes it's important to look at all of them to determine if there's a good place to start in analyzing multiple units. So let's start with the overall process. We start with choosing a basis, which in this case is given to us. We're told that 100 moles per hour enter into the absorbing column. If none of the entrance or exit streams had a basis, then we may be able to choose one as long as it didn't change the values that are given to us for other streams. So to start the degree of freedom analysis, we start with writing out our unknowns. Now we don't know N1, we also don't know N5, nor N6. However, we are given all the compositions for those streams. So those are our three unknowns. So then we write out the species that are involved. We have acetone, carbon dioxide, and air. Now, why don't we include the water? Well, we don't have water coming in or out of our boundary. It's just within it. So we're not looking at those streams. We just care about what's crossing that boundary. So we have three species. But here's one thing to take into consideration. Our air over here, that's labeled as N5, is 100% air, and it leaves at the same flow rate in this stream. So this isn't an independent relationship that we could use in our degree of freedom analysis. So we can't write a molecular species balance for air. So anytime that you have a relationship like this that's not independent, that doesn't help us solve the balances around that boundary, we remove that species from one of the molecular balance species that might help us. So we have three unknowns. We take out the two species balances that we could write. We're left with 1 degree of freedom. So this means that as underspecified, we can't solve the material balances around this system as specified unless we were given some other type of information. So next, let's do a degree of freedom analysis around the absorber. Again, looking at the unknowns, the stream coming in is fully defined. We have an unknown N1 stream that's leaving. We have an unknown N2 stream that's coming in. And then we also have a stream leaving with flow rates N3 and N4. We write down the species that we may be able to perform a molecular species balance on. We have acetone, carbon dioxide, and water. So again, this gives us 4 unknowns, 3 species balances we could write, and we get left over 1 degree of freedom. So we cannot solve the material balances for the absorbing column. Lastly, let's do a degree of freedom analysis for the stripping column. For our unknowns, we have N2, N3, N4, N5, and N6. Again, the compositions are labeled for us where needed. The species that we are looking at for this stripping column are water, acetone, and air. But again, as we mentioned, for the overall balance, we cannot do a material balance for air. It's non-independent, so we are left over with 5 unknowns and 2 species balances that we could write. That gives us 3 degrees of freedom. So for this particular process, every degree of freedom analysis we perform says the system is not fully defined and we cannot solve for any of the unknowns. Since a basis is provided, we cannot assume a different one as one of the variables that might help us. So we would need some other piece of information to complete this problem. Hence, the degree of freedom analysis is important, since we have now realized we need to dig deeper for information or assume something else about this process to proceed.